Right. Another method of measuring level then is capacitive. If you have any sort of thing, if you have two metal rods and you put electric charge between them, the amount of electric charge you can put between those two rods is dependent on the dielectric between them. So if you know the dielectric constant of the stuff that you've got between the two rods, then you'll know how much dielectric there is, because as it rises up the tank, the dielectric changes and the capacitance changes. If you have a metal tank, then the outside of the tank can double up as one of your rods. So that if you have a metal tank, there's the outside of the tank, and your capacitive probe is the other side. And so you're measuring the capacitance between those 2 points. If your liquid is a conductive liquid, so here's my liquid in my tank. If my liquid is a conductive liquid, then all that's going to happen is those two are going to short across. So if I have a conductive liquid, I have to get an insulated probe so that it doesn't just short across. Otherwise, it's not going to work. So if my liquid is a conductive liquid, I need an insulated probe. Oh, go back. Now, lots of people love capacitive pressure level sensors. Personally, I loathe them. The reason I loathe them is because if that tank is 10 meters high, that means that the probe has got to be 10 meters long. That means that if something goes horribly wrong with the probe and you need to replace the sensor, you need to climb up a 10-meter ladder holding a 10-meter probe. And then when you get on top of the tank, you've got to wrestle a 10-meter probe out, and then wrestle the new 10-meter probe in, and then climb back down the ladder with the old 10-meter probe. And if it's one that's been insulated, it doesn't do it any good if you smack it on the side of the ladder. That's why I don't like capacitive level sensors, because changing it in the middle of the night on top of a 10-meter tank is no fun at all. Right, we've already done DP when we did pressure. Now, we'll talk a little bit about measuring the level in tanks using pressure sensors. The first thing I'm going to do is I'm going to measure, now throughout this I'm going to be talking about pressure in millimeters of H2O. So all of the answers I want, I'm going to need answers in millimeters of H2O. So I want it in millimeters, oops, come back, H2O. So I want all the answers in millimeters H2O. Right. Now, the first thing I want to know is, looking at my left-hand DP cell, what I need to know is, what would this DP read when the tank is empty and when the tank is full? And then this one, let's do this one first. When the tank is empty, oh, I've gone fast and squeaky. Hang on a minute. Now my voice is normally fast and squeaky, but is that any better? Okay. Now something goes wrong with the oh, I don't know, some bloody technical crap, and your voice gets all chopped up. It's a little bit better, but still not better. Let me try again. Testing, testing, am I still squeaky? Okay, that's good. Right. Question 1 then. What does this thing read, this DP, what does it read when the tank is empty? And what does it read when the tank is full? If you could put your hand up as soon as you have an answer, and I'll ask you. Now, nobody's answered yet. Does this mean you're having a struggle understanding the question? Ah, you've got it. Okay. What have you got for me, John?
I think I've got 1,962,000 for your your tank empty, because you still got your 2 meters of pressure in your pipe, I'm assuming.
Yeah. No, I'm only looking. So I think you're looking for a hard answer here. And it's not. To give you an idea of what I'm looking for, I'm looking for a pressure in millimeters of water. So when that tank is empty, I've got 2,000. Now, do you see how that works?
Yep, my answer's wrong then.
Okay. So, Shane, have you got an answer for me? When the tank is full, what do we have in? What does that thing read? Yes. So when the tank is empty, it reads 2,000. When the tank is full, it reads 7,000. Easy? Okay. Now what I need to know is, let's have a look at the other DP here. Oh, by the way, we call that a suppressed zero. I don't know why we call it a suppressed zero, we just do. It doesn't matter what we call it. It doesn't matter if you call it, you know, Eddie. It's just something we call it. Personally, I've never been called in the middle of the night by an operator wanting to know if it was a suppressed zero. But anyway. Let's look at this DP over here. What does this one read when the tank is empty, and what does it read when the tank is full? If you get an answer, let me know. Oh, blimey, I didn't have my microphone on. Okay, can you hear me, everybody? Right, the answers are up there. So when it's empty, it reads minus 500. The reason for that is because the bit of water that's stuck in the pipe pulls it downwards. When it's full, it reads 500 less, because there's a little bit of water in that pipe which is pushing downwards rather than pushing upwards. So it reads from minus 500 to 4,500. You'll notice that the range in both cases is 5,000. So in both cases, the difference between 7,000 and 2,000 is 5,000. The difference in 4,500 and minus 500 is 5,000. So I just need to make sure that you all understand that. If you could give me a tick or a smiley face to say that you all understand how that works. Are you good, Eddie? Okay. Right then. Okay, I'll assume you've all understood that and just go think. All objects. Right, I'm going to change things. This time, I'm going to fill it up with salt water. Now, what do I normally have? In fact, very salt water. And it's got a pen. Specific gravity equals 1.25. Now, I've filled this up with brine. It has a specific gravity of 1.25, which is 1.25 times as dense as water. If I filled this tank up now with brine, and all the pipes are full of brine, and everything is full of brine, what is the minimum pressure? When this tank is empty, what does this dP read? When the tank is empty, what does that dP read? And when the tank is full, what does that dP read? So when you've got an answer, put your hand up or type it in, and that'd be great. Okay, got a couple of answers. We've got 2 meters times 1.25, which gives me, I wish I was good at maths. Where's my calculator? 2 times 1.25, 2.5. Oh, that's easy enough. Okay, yeah. So when this is empty then, where's my pen? When this is empty, it reads 2,500 millimeters H2O. Okay? Because we've got 2 meters of pipe, and 2 meters of pipe, if it was full of water, would give me 2,000. But it's full of stuff which is 1.25 times as dense as water. So it gives me 2,000 times 1.25, which is 2.5, or 2,500. And when it's full, if it was full of water, it would give me 2 plus 5, it would give me 7. But it's full of stuff which is 1.25 times as dense as water. So when it's full, it gives me 7,000 times 1.25, which is, I'm hoping you're right, 8740 millimeters H2O. Right, so if somebody, hopefully with a calculator, has jumped ahead, you can tell me about this side here. What will this dP read when it's empty and when it's full? Okay, we've got some answers. So let's have a look then. Normally, if this was full of water, when it was empty, it would read minus 500. But it's not full of water. It's full of stuff which is 1.25 times as dense as water. So empty, it would read minus 500 times 1.25, which is minus 625 millimeters of water. Now, when it's full, it would normally read 4,500 millimeters of water. But it's not full of water, it's full of stuff which is 1.25 as dense as water, which means it reads, what, 5625 millimeters H2O. Is everybody completely happy with the way those workings work? Because the next one is a hard one. So if anybody wants me to go through this, right, okay. All right. Now, John, I will, what, do you want to, have you got a microphone?
Yeah, just keep going, mate. I'm just a bit stuck on the equations, mate, but you're all right. I'll go through it with you later, mate. I've got it highlighted, mate. I'll go through it later.
Okay, then. I'll carry on. Right, now we're going to get tricky. What I'm going to use is a couple of things called sealing pots. Oops. Now, what a sealing pot is... Oh, that didn't look good, did it? Draw that again. What a sealing pot is essentially, it's a pot with a diaphragm through it and a couple of pipes coming in, a pipe in and a pipe out. One side of the sealing pot is filled with whatever liquid we're trying to measure. The other side of the sealing pot is filled with something that's pretty inert. You see, you do this if you don't want to get the nasty liquid into your sensor. So we'll fill the other side of the sealing pot with something like silicon. Now, silicon has got a specific gravity of 2. So I'm going to go back to having water in my tank. So this is just water, which has got a specific gravity of 1, just to make life easier. But this time, I've got silicon in my pipes, and that's got a specific gravity of 2. Now this time, when we do the empty calculation and the full calculation, for the left-hand DP cell, when the tank is empty, the only pressure being applied to that DP cell is from the 2 meters of pipe over here. This 2 meters of pipe. Now that's 2 meters of pipe, which would, if it was full of water, be giving me 200 millimeters of H2O pressure. So I'll just write that in. 2,000 millimeters H2O. But it's full of stuff which is twice as dense as water. It's got a specific gravity of 2. So the pressure I actually get is that times 2. So the pressure I see when the tank is empty, I see 4,000 millimeters of H2O. Now when the tank is full, and this time it's water, when the tank is full, I see that 4,000 millimeters plus an extra 5,000 millimeters, because there's 5 meters of water in there. So the full value would be 4,000 plus 5,000. So full equals 9,000 millimeters H2O. Okay. Going over to the other side then, when the tank is empty, the only pressure I see is from the little bit of pipe here. The only pressure I see is from the fact that there's pressure in this pipe and it's pulling downwards. And the amount of pipe I need to worry about is the 1/2 meter. So I see 1/2 meter of pressure, and it would be and it's downwards, so it's 500 millimeters H2O. That's what it would be if it was full of water. But it's not full of water. It's full of stuff which is twice as dense as water. So it's going to be that times 2. So the minimum pressure I see is minus 1,000 millimeters H2O. The maximum pressure I see is going to be whatever it is I started with plus 5,000 millimeters because the tank is full. So that's the minimum is minus 1,000. The maximum will be plus 4,000 millimeters H2O. Okay? So we commonly use sealing pots. It gives us a way of isolating whatever nastiness is in the tank from our DP cells. Water is quite destructive to DP cells. Brine is very destructive to DP cells, so we'd use a sealing pot to keep it out of the DP.